Hi gang, sorry for the abrupt ending. Had a technical glitch, and I didn't really want to delete the 12 minutes or whatever it was. So where are we? Well, we have a mean that is unknown, standard deviation known, and from work done by previous statisticians, the underlying probability distribution that models this phenomena is the z distribution. All right, so the central limit theorem kicks in, and again, in a nutshell, what does the central limit theorem and sampling distributions tell us? Well, it tells us how all samples are going to behave. So if we dive into this distribution, again, what do we know about it? Well, we know that it's going to be a normal distribution. Smack dab in the center is going to be the mean, the population mean, which we are looking for, we're trying to estimate. And we know that the variance is going to be defined by the standard error, which is sigma over the square root of n. Okay, so what are the measurements here? The individual measurements here are sample means. So what we do is we come in and we collect a sample mean at random. We know that 95% of the distribution of sample means around wherever this thing is centered fall from 1.96 standard errors below the mean to 1.96 standard errors above the mean. So we take this estimate in general and we add and subtract margin of error, because again, we know that these sample means fluctuate. There's nothing holy about this one. This just happens to be the one we're taking to the dance. So we're going to come in and we're going to build, if we can imagine this width right here, we're going to shift that over and create an interval around this estimate. Okay? So there we're going to have x bar. As I said in the previous video, the margin of error is defined by the z critical value times the standard error. So this will be x bar plus or minus z critical is 1.96 if we're focusing on a 95% confidence interval. And the standard error, of course, is sigma over the square root of n. Now, we are 95% confident that this interval contains what we're trying to estimate. Why? Well, because any sample mean from this point to this point, if we build this interval around it, it will contain this value that we're trying to estimate. The only time this interval won't contain the value that we're trying to estimate is if we get something out here or something down here, for obvious reasons. So again, we select one at random, this one, whichever one of these. There's a 0.95 probability that this interval that we build around it, based on this 95% proportion of sample means in the sampling distribution, will contain the value that we want. All right, so how does this work in practice? So let's just say, let's dive into R. And I have a data set. I should have already had this done, just didn't. All right, so I want to get my data here, and I believe I called this admit GRE. Hope I did, yeah. So let's just look at the head of the data and see what we have. So we have IDs. Again, this just shows the first 6. Then we have an admit, which is yes or no. We have a GRE score, and we have a GPA score. So for the sake of this illustration, let's say that the the GRE is specific to a large school university. And then the mean GRE is unknown, but let's say that sigma is known. So to calculate the 95% confidence interval, we need three things. X bar, Z critical, and the standard error. Now, so to get the mean, we have 587.7. If we're focusing on a 95% confidence interval, then the Z critical is 1.96, as we saw previously. I'll show you how to change that. And then the standard error comprises of the population standard deviation over the square root of n. So I need 587.7 plus or minus 1.96 times 110 over the square root. So we need our sample size, and we can just do length of any of the variables. Let's just do GRE since that's the one we're focusing on. So we have a sample size of 400. So put this in our calculator. They're really very, very, very easy unless we do something really goofy. So I just put that in my calculator. Obviously, I'll show you how to do this in R. So 576.92 is the right, and then I'm just going to come in and do entry and just change that to a plus. All right, easy stuff, right? 598.48. When I say 48, forget. Yeah, and I'll tell you the reason I'm going into so much detail on this is as director of this program and as a professor in the department, I observe a lot of College Credit Plus teachers, high school teachers, and I see them teach the central limit theorem and make a connection to confidence intervals, and I'm not really very happy with the way that they do that. So it shows to me that there's some underlying gap or disconnect between estimation and the central limit theorem. Okay, now we also have the central limit theorem and sampling distributions are helpful with categorical data. So let's say that the unknown here is P, which is the percentage of applicants that are admitted. So we'll estimate P from P hat, which is the number of applicants that were admitted divided by the total number of applicants. So we know that this will be out of 400. And we can come over here and just do table admit. So there were 127 out of 273. So 127 out of 400 tells me that my point estimate is 0.3175, I believe. Yeah. So what happens? Central limit theorem kicks in, right? We know that the underlying probability distribution is going to be centered around P, the unknown percentage. Adjust this just a little bit. There you go. And the standard deviation is going to be the square root of P hat times 1 minus P hat over n. That'll be the standard error. So let's calculate a 90% confidence interval for P hat. Well, a 90% confidence interval is going to have a different test statistic than P, because if we have a 90% confidence interval is going to have a different Z critical than a 95%. So if we have 90%, we're missing 10%, which tells me that 5% has to be in this tail and 5% has to be in this tail. So to identify this value right here, I would use Q norm 0.05, 0, 1. So negative 1.645 is this Z critical, and obviously 1.645. So here's where we get the plus and the minus. So our confidence interval looks like this. Again, our estimate plus or minus our Z critical times the standard error. Specific to this type of problem, our estimate for P is P hat. Our Z critical is 1.645 because we're estimating at 90% confidence level. And our standard error is P hat times 1 minus P hat over n. So we know our P hat is 0.3175. 1.645, 0.3175, so this should be 0.6825, right? I hope so, over 400. So grab your calculator, and that should be, I wish I could fast forward here, but I can't. So I get that. Hopefully I put everything in correctly. So 0.279. And just make the change from negative to plus 0.356. So people typically think better in percentages than they do proportions. So we're going to say that there is a 0.9 probability that this unknown P or the 0.95 probability that that interval contains the unknown value for P. Notice it's centered around our estimate of P hat, which is 0.3175. All right, all I got for this video. Take care.